My name is Brice Loose, and my specialty is geochemistry with a focus on Arctic systems. And so I'm funded to participate in MOSAiC throughout the course of the year to basically observe some of the microbial carbon cycling that takes place in the ocean, but also in the sea ice. Specifically, we're interested in the role of microbes and also in ocean circulation in oxidizing methane in the central Arctic over the course of the year. So I think we can frame basically the major objectives of these working groups as, in a very broad sense, with the question, what happens to ecosystems and to ocean biogeochemical cycles in the new Arctic? And that's a very broad question, but I'll try to bring it down to some more specifics as follows. So we know that we've got demonstrable proof that, for example, the Arctic is warming, that the ocean is warming both in the continental margins and in the surface ocean, but also in the deep ocean as a result of intrusion of warmer water masses from adjacent seas to the further to the south. We also know that the Arctic is experiencing a dramatic thinning in the sea ice, so this is actually a reduction in the sea ice thickness, which takes longer to grow every year and melts back earlier every spring and is also more translucent. In addition, we see a lot more fresh water and stratification in the upper layers of the ocean, and this has a tremendous impact this is basically in the same region where sunlight penetrates the ocean, and so primary production and most of the ecosystem is oriented towards this area, and that's where we're seeing significant impacts as a result of that. Then, of course, a thinner ice cover is also weaker structurally, and so it's more potentially fractured and dynamic, which basically creates both ridges and keels in the ice as the ice comes together in some places. But where the ice is compressed, there's another region where the ice is basically under decompression, and that's where you get openings in the water, such as leads. And finally, emerging hazards. For example, we've identified that plastic is a significant hazard that we're trying to observe during the MOSAiC drift. So let's begin with temperature. This is a map of the sea surface temperature that was compiled and released in September of 2019. And you can see that basically there are something like almost in every marginal sea and throughout the Arctic, doesn't matter which section of the Arctic, there's almost 1/10 of a degree C warming every year. And so this is a very significant trend. This is not seen anywhere else in the entire global ocean right now. And so the transformations are just breathtaking. And if we consider that this affects for the ecosystem, then we might need to evaluate, for example, the migration of fish species. And so this is a major part of the MOSAiC activities throughout the course of the year, is essentially to create like an environmental census of all of the different trophic levels, not just the plankton, the phytoplankton who do the primary production, but the zooplankton which eat the phytoplankton, and then of course the juvenile fish and eventually the carnivorous fish, and how all those trophic layers stack up over time. Because we want to know, are we basically creating a new ecological niche in the Arctic that species from the south can actually expand into and take advantage of a habitat that they weren't previously able to occupy. And so another really important connection to the warming that we see is what's happening on the shallow marginal shelves. So as you may know, the Arctic is surrounded by shallow continental shelves. Something like 2/5 of the entire Arctic Ocean surface is these shallow margins. And so because they're shallow, they cool off very quickly in the wintertime, they lose all of their heat, and they rapidly begin to produce a lot of sea ice. That sea ice production in turn creates a dense cold water mass which sinks into the central Arctic and produces the water mass which is known as the Arctic halocline. So this is a very important structure that exists in the oceanography of the Arctic. It both separates the warm Atlantic water from the surface layer, but also is a conduit that basically carries material from the shelves into the Arctic Ocean interior. And so if we start to see warmer water, less ice production, we're potentially going to see less production of this dense water entering into the Arctic halocline, and possibly as a result a reduction in the halocline, which might be compensated by an intrusion of more warmer Atlantic water. And so in the same, basically in a coincident region to where we're seeing the warming on the Arctic shelves, this is a region that's actually full of greenhouse gases. So the Arctic sediments basically all along the continental shelf and into the shelf slope, these are areas that are replete with methane and other hydrocarbons, which are stored inside frozen structures, basically like a hydrate ice or a permafrost material that basically traps that organic carbon in place and keeps it there essentially inert and stable, but it's only stable and inert as long as the conditions are right for that situation. So it requires a certain temperature and water pressure. And if we start to increase the temperature a little bit, we can see potentially a destabilization of this large reservoir of greenhouse gases, which will subsequently evolve into the water as bubbles and then potentially into the atmosphere. Okay, so those were all processes that we connected to the warming in the Arctic that we're seeing, specifically the warming in the surface ocean, but also in the deep ocean as well. Now let's talk more about the thinning sea ice and the increase in the freshwater and stratification. So these are important factors for the ecosystem because they potentially change the radiation budget. You can have more light penetrating through the thinner ice, but also you have a stabilization, potentially you have different components of the ecosystem trapped at different layers in this very stratified water column. And we don't know exactly what the outcomes of that will be, but this is something that we're out to explore. So you may have learned in the life in ice and in the adaptations to sea ice that when you form basically ice, which is a pure solid from an impure solution, you essentially have this process of what's known as solute exclusion. So as you form an ice crystal structure and the hydrogen bonding becomes more ordered, certain compounds like sodium, for example, and oxygen are excluded from that freezing matrix, and so they become more concentrated in the remaining water, but they're not found within the ice. And so when you extrapolate this down throughout the freezing process, then what you observe is the ice, this sort of salty water that's left behind, which is known as brine, ends up becoming included along some like ice crystal grain boundaries. And over time, this creates essentially like a capillary structure or a porous microstructure within the ice. This ends up being very important to the way we conceive of the ice. This porous microstructure has important chemical properties. It also has very important biological properties. So, and we even actually start to see not just the aggregation and growth of macrophyte algae on the bottom of the ice as a result of this porous microstructure, but we also see individual organisms being incorporated into the ice. And they've, of course, as you learned, they've developed these techniques to survive in this very harsh environment over the course of the winter. And then they play, we think, a very keystone role in the spring bloom, which evolves as the ice retreats in the springtime. So if you imagine then ice that's been evected potentially from a continental shelf that might be full of sediment, that has some micronutrients like iron and manganese, it has some ice algae incorporated into it. When you deposit all of that in the surface ocean, as the light comes back and the ice is melting, you have all the conditions that are necessary for a significant spring bloom and even potentially an under ice bloom, which is something that we're starting to see when the conditions are right. We've actually undertaken a very ambitious sea ice sampling goal. So every Monday throughout the entire MOSAiC drift, the teams from the Biogeochemistry and Ecosystem group, they go out together with sea ice and they collect up to 60 ice cores. And they bring those ice cores back and they process them for a whole suite of ecosystem and biogeochemical parameters. These include dark organic carbon, they include the bacteria that consume that carbon, they include the nutrients that are dissolved in the ice, they include volatile organic compounds like dimethyl sulfide, as well as methane and CO2 and N2O. They also include different organism taxonomy. But in addition to that, we've got some more targeted projects where we're actually trying to explore the role of specific features in the ice column. So this project, for example, which is started by the Norwegian Polar Institute, it's called HAVOC. So the HAVOC project basically postulates that if you have a thinner ice cover overall with less basically undulations and refuges, then every keel and every ridge system that's produced becomes an even more important, essentially, habitat refuge for all of the organisms that are essentially trying to hide out from predation and access food. So this would be plankton, this would be juvenile fish, all of the organisms that need to essentially hide from predators, but also be able to be in the proximity of a biological hotspot. Okay, so all of those processes that I was just referring to are connected to the thinning ice and to the increased stratification. Let's talk last now about what happens when you have a more fractured and dynamic ice pack, as well as the emerging hazards. So one of the consequences of a more fractured and dynamic ice pack is that you have greater light penetration into the ocean surface. But also, as I said before, if you compress the ice here and essentially create a vertical structure, then what you've done is you've removed ice from over here, And so you've created a lead or a polynya, some structure that will allow the ocean surface, even under very cold conditions, to be directly in contact with the atmosphere. And this is a very important process for the aerosol production, which you learned about during the MOOC, but also a very important process for some really complicated halogen chemistry, which happens in the atmosphere. And so last but not least, this is something that we've observed maybe even more recently in the Arctic than in other places. It's increasingly apparent that the Arctic Ocean is not as pure as we'd like it to be. We think that there's plastic being advected in with the ocean currents, but also being lofted in through the air. So we have studies showing that plastic is being deposited in snow as a result of air masses that come from the south. So MOSAiC is carrying out a year-long time series to basically collect samples for plastic and observe that. And so we hope to basically take this year-round suite of measurements about all these different components of the biogeochemical and ecosystem parameters and essentially feed those into the development and improvement of process models, which will be able to give us a really detailed predictive understanding of how the Arctic system functions in this new state where we've really moved away from the previous state where persistent ice cover and thick ice cover, which lasted for decades in many cases, has gone away, and now we're in a situation where the ice basically freezes out and melts back every year. And we think that this will tell us not just how the Arctic is going to function in the next, say, 100 years, but also how its role in the overall Earth system, which we also know is very important, will evolve.